Le nom en plus était centre INRIA de Bordeaux avec Pau, donc de Pau et des pays de la Dour, tout à fait. L'équipe INRIA s'appelle CAGIR. Donc on n'est pas beaucoup de membres. Historiquement, ils travaillent plutôt sur le turbulent, et donc moi j'apporte la touche multiphasique à l'équipe. Bonjour à tous d'ailleurs, hein, en passant. Merci pour l'introduction. Donc aujourd'hui, je vais vous présenter donc des travaux que j'ai fait récemment, et donc principalement avec Luc Biazori-Poulange, qui est à ETH Zurich, dans l'équipe de outils Supponen. Et donc, ces travaux portent sur des effets de cavitation qui apparaissent suite au passage d'un choc dans une goutte. Et donc, on a fait ces études en utilisant une approche multiphasique que je vais vous détailler. D'ailleurs, pour être sûr, en français, tout le monde, c'est bon. Je ne sais pas s'il faut faire en anglais. Les slides sont en anglais. Bon, faut pas hésiter. Ah, très bien. OK. I continue then. So just a little bit of context. So in general, we are familiar when we talk about multiphysics, multiphase, compressible flows. I like to bring this slide because there's a lot of applications that come in mind, right? Come in mind, like for aerospace or naval applications, where there's cavitation, for example, here around the blades. There is also like defense applications, but what is less known, and I will talk just slightly a little bit of this today, is biomedical applications. I will give just a few examples of this. But before that, I wanted to bring a little bit of like a taxonomy about the modeling of multiphase flows, but more or less here in the context of cavitation and bubbles. So if we look here, we can see that there's different approaches. On one side, on the left, you can see that there is the approach where we resolve the interface. When we resolve the interface, meaning that the mesh is able to capture the interface. There's two other branches here where you have like the fitting approach. So for example, when you have the Rayleigh equation type of modeling, and you have the what is called the capturing, where so the mesh captures the interface. On the other side, you have what is called the mixture average modeling. So this is more an approach of really multi-phase mixtures. So in these two, you have the homogeneous approach, meaning that everything is homogeneous. There is no geographical point of view in this approach. So it's a real mixture of just particles mixed together. And heterogeneous, so for example here for bubbly flows, where you have bubbles that are actually models within a mixture. So here you have some examples, for example. So I like this one, for example, so which was in the continuity of Daniel Fuster's work, where you have some Lagrangian particles that follow, so the particles, it's Lagrangian bubbles that follow a Rayleigh equation, and then you have an Eulerian framework with the source terms that make the connection between the two. And so what I will present today is a little bit between the two approaches. So if we continue on the capturing side, there is what is commonly known as sharp interface. So what is usually done for incompressible flows, but also for compressible flow, like we can see here in the lab actually. And on my part, I use what is called also the interface capturing or diffuse interface method, which is at the edge between the two big type of approaches, where so the interface this time is diffused, right? You have a mixture region between the two. And if we take an homogeneous modeling approach, and if you resolve it enough, then you can reproduce the same type of behavior. You still have a mixture between two pure fluids. Just a little bit of, if I would say, about ECOGEN. I will be short on this, but all the results I will present are based on the software ECOGEN, which is a software that I've been developing for years now, which is a collaboration between different institutes. It started in Marseille at UST, and then it followed for different with different institutes. And so this code is able to multi-phase compressible flows. And so initially, the idea was actually taken. I hope it was the same spirit, but it was really inspired by what did what both either with or with Basilisk risk. Okay, we and the fact that research is the public research is going forward for like broad for broader community, right? So we wanted to have this spirit initially, and then collaborations came along. So this is based on finite volume method. We have different models, physics, such as viscosity, surface tension, mass transfer, different type of meshes, and obviously it's parallel. And what about the applications? As said that I'm going to talk a little bit about biomedical applications, but first, just an idea about previous studies that we have done that I found really interesting about atomizations, Droplet cup, where we did a study where we particularly looked at how a shock wave and flow and produced by the shock wave can disrupt the interface of a liquid droplet and progressively create instabilities at the surface and have a filament and then fragment in little pieces. So we did some instability studies here. You have also done by with the CNEST about cavitation in turbopump. So this is a liquid oxygen coming where you have cavitation appearing near the blade. And what about the application that I like? Is, one collaboration I did with a company in the US is about using microbubbles and ultrasound with a low intensity ultrasound to treat kidney stones or urinary stones. So the idea is to have this low intensity but high frequency ultrasound will interact with bubbles, and this interaction with bubbles will focus to the stones, producing jets to the stone, and progressively actually and break the kidney stone. So we've done different studies on this. First here with just a flat wall, then with some crevice. Another interesting study I like is about an injector device. So if you have some, it's all. Oh, which one? It's all ECOGEN, and this one is experiment. So everything was made with ECOGEN here. Yes, and it's open source. So even if you just want to give a try try yours, I mean, it's completely free. Auto indoor device. So if you have some allergies, you have some system, some device that you can push directly into the heart to give the medicine. And when you do this impulse, you have a plunger here with a rod that will push a plunger, and this plunger will send a big compression wave through the syringe. And when you actually hit the body, there is a tension wave going up within the syringe. You may have cavitation bubbles here appearing, and then these cavitation bubbles are compressed by the compression wave and may actually break the cone here of the syringe. So I could go into detail later if you want about this, but this was an interesting study did at Caltech. And then lately, so I didn't work on this. This is a work from ETH on still for drug delivery this time, where you try to encapsulate a drop within a bubble, and the idea is to try to say, okay, now if we push, we send a wave and to this bubble, will the bubble collapse and hence the fragmentation of the droplet? So is to atomize the droplet which contain the actual medicine, the drug. All right. But the numerical method. So finish with the head and let's go into the actual problem. So there is different type of models that exist in the situation of multi-phase approach. So I'm not talking about sharp interfaces, right? Like multi-phase approaches. If you take the context of two-phase flows, what is commonly known as a 7, 6, 5, and 4 equation model. And basically what it means is that for the parent model, what you have is you have a complete disequilibrium between the phases. Right? You may have you have terms that will produce equilibrium if needed, but by nature initially they are at disequilibrium, meaning that phases together, like a mixture of phases of two phases, are in temperature, pressure, and velocity disequilibrium. And if you go to the sixth equation, you reduce, you have now just temperature and pressure, so there is a velocity equilibrium this time. The 5 equation model now has a equilibrium of pressure, and then complete thermodynamic equilibrium for the last one. And so in this presentation, I will focus on the 6 and show a little bit the equations related to this. So I talked about the 5 and 6, right? So why do we use the 6 equation model initially? So if we want to treat an interface problem, you want to make sure that the pressures and the velocities are the same at the interface, unless you have some surface tension. And so this is commonly used and with which is well posed mathematically, but also in terms of thermodynamic, is what is the capillary model. So in this one, you have an equation on the volume fraction, equation, well, two equations, so one for each phase mass, and you have a mixture equation for the momentum and a mixture equation for the energy. And what you have with this model, which is an asymptotic limit of the 7 equation model, right? And when you have this term, when you do the asymptotic limit, you have this term that appears, which is called view, and this term accounts for the expansion and compression of phases within the mixture, right? So if you send a wave like through a mixture, if you have bubbles, will compress, so the volume will be reduced, and this term represents this effect Otherwise, it's just a transport equation. The difficulty here is that this term K here is non-zero in a mixture or at the interface, because the interface, I recall, is a mixture. So this term is non-zero. And then you multiply it by a divergence of u. So if you send a shock wave on an interface, so the divergence, as you are fine, tends to infinity. And you have a non-zero term times infinity. So this term is actually very problematic for robustness of the code. Which is why it's not really used in here. But if you don't use this term, then you have you break the second law of thermodynamics, and also when you actually do some cases, you don't represent those effects. And for example, for bubble collapse, you don't have the good behavior. So what we do is we use a 6 equation model. So this is the model, the first parent, right? So instead of having the energy equation for the mixture, we have 2 equations. One for the so 2 equations for the energy, one for the liquid, one for the gas. Here expressed through the internal energy, not the total energy. And on the left, you have some what is called pressure-relaxation terms with a pressure-relaxation coefficient. And those terms basically represent what is the effect of compression, so the same effect on the effect of compression expansion of phases within a mixture. What is as you do mathematically an asymptotic limit, or if you do it numerically, if you tend mu to infinity, then you have an equality of pressures, and so you can verify this, that mathematically and numerically, and this model exactly converge even numerically to this model. So you have the same results, but you have the good thing is robustness. So this model is super robust, like it's almost never crash. In Mach in 2009, so this was a way to compute the capillary Knoll model. Okay, so now if we talk just a short slide about what are the numerical methods we used to solve this model. I won't extend too much on this, but we use some Grunov type interfaces. We solve problems. In our case, called the HLLC Riemann solver, so approach. And we are always constrained by a CFL. We use some second order muscle scheme, and we always solve a system of ODE, which this system is basically once you solve all the terms linked to the hyperbolic system, then you have this you have those terms here, and then you only have the ODE system with the relaxation terms to solve. Okay, so last year, I think the paper was out beginning of the year, but the work was mainly done last year. At some point, we wanted to, for different reasons, to be able to have a finite relaxation instead of an infinite relaxation, what is done today. And the method to solve this, the model that was proposed by Sorel in 2009, was not able to do finite relaxation. Actually, you were it was mandatory to use infinite relaxation because the way it was constructed, it was difficult. So what was directly done is you had an hyperbolic step, as I said, an infinite relaxation procedure, and after this you had a total energy correction scheme for the internal energy equations. So what I mean by this is we have our 6 equations, but we always solve an extra one, which is the mixture total energy, because as you can see, these internal energies have non-conservative terms, and so you cannot assure numerically that this will be always perfectly uh, um, conserved. Mathematically, it's conserved, right? If you sum everything, you end up with this equation, but numerically, it's something else. So, and to do so, as I said, the total energy correction was done after the infinite relaxation. And so what we proposed, and he actually took us more or less 3 or 4 years to do this, so it seems nothing, but it was actually a very long and difficult work to make sure that we can now have the new total energy correction scheme embedded within the hyperbolic step, and then it allows to have the infinite as well as the finite relaxation procedure. So the relaxation system, as I said earlier, basically solves these two equations. Well, you have 3 equations, so alpha F, one for one of the volume fraction, and then the 2 pressure. So this was done in collaboration with and when we started to work on this shock induced by a shock, and then we realized that somehow the approach that was it's not for this model, it was like for always where what is initially the very parametric cell called mu kg, so it's like represented taken as somehow you are not able to cover a mixture well pretty good. This don't record exactly the behavior of a leak of what a mixture should be like what mixture I will see. Didn't work. Saying okay, what about if we get this ID that is fixed for like now about kg. This is the concept for a system, and it should be mu, right? This if I translate that represents like the time that it's the unit of time. This one, so it's time needed is whether if they are in the equilibrium, all need to what was done historically always one is infinite. So what are the expression here? This, but that it's instantaneous, right? So you send a wave through a bubbly flow directly, it's in equilibrium, right? But we represent exactly what happened in physics. It's the case. So we say, okay, we still want the multiplication of two functions. So this expression allows outside of the consistency of the system, what is not is specific behaviors can let's say the phase you want phase which right so you will time for the bubbles and liquid which equilibrium. So let's say more or less fraction of bubbles to -6, let's say, then this term is about 10 to -6 because one of the alpha is 1 minus. So you have what term about 10 to minus sometime. Say 2 phases is approximately the same volume fraction, so it's equal to 0.5. So you are at an interface, and they are very close to each other. Once we communicate a lot, right? Basically, one when a rebound, and the other ones as communication too. And so if you do so, then you only multiply by 0.5 square. So you end up 1 instead of 10 to the minus 6. We produce have very fast communication. So it's basically, so if interfaces communicate, they reach equilibrium. The third, let's say you have and when you have 3 phases, you have terms basically, and you, so through the interactions between the 2 phases, which let's say the both when basically really to it. One, in a well, so but I won't talk about this today. So this one was our cavitation from now explain a little what I mean by this cavitation, the phenomenology. So let's a shock impinging on a drop. So we took a cylindrical drop because that's where experimental data. So you see what within a drop, meaning a because well, simply because the signal you try to recover the interface disturbs the signal, and you cannot get anything from the experiments. Experimental data from a cylindrical droplet. So when you send a shock wave, a big part of the energy, because of the impedance differences, a big part of the energy rebound and so bounce back on the droplet. So we didn't do the bounce, the outer part, so the shock wave. It's not a problem, but some part of it will be transmitted to the droplet. So some part of this energy is transmitted, and you have the incident. We don't have, and this incident shock wave, which now is traveling within the droplet, well, faster than in the gas due to the speed of sound. And as soon as this compression wave reaches some part of the interface where you have now a different, right? It's a different situation. It's not a wave in gas, really impinging on interface with is the opposite. So if you have a wave within gas impinging a compression wave in liquid impinging on an interface with air on the other side, it will bounce back as a tension wave. So then you have these tension waves that progressively happen within the droplet. So initially you have a shock wave, compression wave, then transfer to the droplet, and when it bounces back, you have a compression wave. This compression wave if the shock initially is sufficiently strong, meaning the compression wave is sufficiently strong, the tension waves will create bubbles here. So you will have cavitation at these particular places. And so you continue, you have more bubbles, more or less collapse, concentration, and you have more bubbles until you have a big, let's look at. Then the waves continue their interaction, and this cloud potentially collapse and create its own shock wave. Okay, so presented here, all these lines are done with analytical wave description, and they are based on the assumption, of course, that it's a pure liquid, right? So they are not taking into account the fact that bubbles interact and it may disrupt this. So if you, so this analytical wave description is basically based on some ray tracing of acoustic waves. And if you do so, you may end up with some these curves here that are called caustic, which are the points at where like waves are merged. And this caustic then at the end exhibit a cusp, C, which was supposed in the literature that this is the maximum, this is the point of maximum tension. So if there was cavitation, this is where the cavitation should happen. So now if we look at so and what if we compute for different, so sorry, mu equal here 10 and here, so we compute different pressure relaxation rate, then Mach 2.4 and the droplet 2 in diameter. So we see a wave traveling initially within the droplet, and in dash is a caustic, right? So what I just shown in the point of convergence of the two tension waves. So wave continues. So between the three, we don't see much difference, although here we start to see some perturbation here. So actually, this is because this one is to some kind of infinite fixation. So as tension wave, there is some bubble, because with the droplet I didn't mention, we put some volume fraction of gas, which is about 10 to minus 6. This is a mix, almost purely. And as soon as the tension wave start to some significant negative pressure, you have the growth here, right? So, and this tension continues, and if you here at this, for example, you can see that cloud here. So it's run images, so we see the contour of the cloud of bubbles here. The big cloud of in the drop. This the bubble doesn't have, they take too long to equilibrium with the liquid, don't grow, and so here, but then in the compression there is some equilibrium that is reached. So basically, by the time they try to reach to grow, they are just compressed, and so they find some equilibrium. So if we look at this low mu, then we can have we are able to recover almost exactly the analytical solution. While if you are for mu that is relatively large, you have a bubble, a cloud here that will collapse even before the one with 10. So you have a big cloud here, no bubbles at all here, and here more or less between. And what about when we compare to experiment now? So when you compare to experiment, so if you take the mu equal 1, so this is experimental image. So this is a Schlieren image, but when you do a Schlieren, you see the shocks, some kind of shocks here, some kind of waves, obviously. And I recall that when you do a Schlieren image, experimental Schlieren image, the cloud here is basically just a black point. So there is no contour like we have. Actually, that when we do a gradient within simulations. So we have a cloud here of bubbles. And so we have the same waves here, right? We see the same structure of waves in the experiment, but we see the cloud that we don't see here. And there is also extra waves here that actually are the shock waves emitted by the collapse of the cloud. So this cloud is already in the rebound phase. If you go to more or less what is historically done with mu is equal to infinity, those waves were completely absorbed. So the tension waves that bounce back everywhere. So I didn't really mention this, but here you see those waves here are completely actually absorbed by the growing phase. So there is no tension wave anymore here traveling within the droplet. There's only this. Everything was absorbed by the cloud, by the bubble cloud. And so you see the cloud here, not at the right location though, but you see the cloud, but you don't see the waves. And if you take mu equal 10, you see a cloud that already collapsed, so you have some shock waves here, but see it's not aligned with the shock waves already there. We don't see the other waves also. So these images are based on Sembian, all the experimental images. So we see that we must be close between these two, right? We want the cloud, but we also want those waves. So by using the experimental data, we have some time frame, so we know that the cloud must be between these two timestamp. So this time and this time are just like the time resolution of the experiment. And we also know the location of the cloud by looking at the experiments. So we found that mu should be about 3.5 here. And if we do so, then we are able to recover the exact same dynamic. So we have the waves, we have the cloud, we still have the waves here, and we have more or less the same contour of the cloud in the same location. And we have we don't really see well the shock waves here emitted, but I can tell you they are here. So we see basically everything that what is seen in the experiment. So once we did this, we were like, okay, so we know that mu 3.5 is good to represent the good phenomenology. So this is basically the good characteristic time for a mixture to actually find equilibrium, mixture of liquid and gas. And we have some experimental images that were done for Mach 1.75, and at this Mach they didn't observe any cloud. So we were like, okay, so what if we try with this mu 3.5 this Mach, and we didn't also observe any bubble cloud. While if you use what is commonly used in the literature with a mu that is infinity or other models that are in equilibrium, like homogeneous mixture model, you will observe a cloud that is almost as big as the one that is supposed to be for Mach 2.4. So we were able to see to have the same observations with the new simulation than both of the experiments. And we were also able then to find, okay, what is a critical Mach number for this experiment, where we actually start to see cavitation occurring within the droplet. So we found about like between 1.9 and 2, so Mach 1.9 and 2. So infinity, sorry, is a dashed one, and these are the mu equal to 3.5. So then we were like, okay, so we found a mu, and now what about if we take another experimental data that is in literature, and this time it's not a liquid drop, like it's not pure, let's say pure. It's not water anymore. It's a gel actually. So this you have a gel. So they need gel because you have so it's still a cylindrical droplet or cylinder between two plates of glass, and you need gel to make sure that this one is not moving. And then you impinge this one with a plate. So you have a gun firing a plate. So this plate is aluminum, and this big plate of aluminum is impinging the droplet. So you have two things here. Then it's not water anymore. It's water with some gel. So if I remember well, it's aragos. So you have a different mixture that also have bubbles with some nuclei within the mixture, because you always have nuclei within the liquid. But also the regime is not the same, because we are about few megapascal for the previous case. Here we are about gigapascals. So the regime is not the same, and the mixture is different. And what we observed is that we were not able with mu 3.5 to observe the experimental data. But if we change it a little bit, we found that with doing the same process that we did for the previous one, we found that if we use mu equals 0.5, then we are able to find to match relatively well the experimental data, both on the waves, the location of the clouds, those small peculiar things here happening. So we ended up saying, okay, we need some like a approach, like a deeper approach, experimental studies where we can very control things, control the regime, control the mixture, and this is something we are going to do for the following year. So because as you can imagine here, we don't know if the regime is important, but we know for sure that if you have a gel, it will trap some bubbles within the gel, more than if it's just water from the tap, right? So we know that there is an influence here, but we don't control the initial volume fraction. So we want more control and find, okay, what is happening when we control everything, and can we find like good parameters? So we have a tool that we know that we can use to find what's happening in mixtures, so real mixtures, but we need more studies to actually understand better what is happening. In conclusion, we use the multiphase approach with a new formulation for the pressure-relaxation terms. We studied even though I didn't explain that much, but we studied the phenomenological study here. So we did this on the shock-induced cavitation. We found that there is only one unique relaxation rate that matches the experiment. So meaning that is able to reproduce the real multiphase phenomena. I didn't present it here too much, but we found that the analytical predictions that is known in the literature to say cavitation should happen here is not true. There is some error here, so we corrected this by some relations to say, okay, when it should happen and where, so to find the bubble cloud center. We found also the critical Mach when cavitation occurs, and here are some open things that it still remains to do, like I said. So future experiments to then say, okay, if we vary the regime or the mixture properties, like some viscoelasticity, so because we know that viscoelasticity matters, spatial arrangement of molecules might matter, so all the nuclei are proposition, the concentration, and the size of the nuclei, so everything that, all those specific things matter, and we have no control here on the experiment. So we want to do our own experiment and control those aspects. And things that we don't know yet is like, okay, I didn't mention it, I'm sorry, I should have, but we don't have phase change here. So yeah, what we see the growth is only the fact that a gas phase don't have the same response to a wave from compared to a liquid. So it's just the difference of response from both phases. So one is more compressible than the other. And just this response produce big differences in terms of bubble cloud. So even if we look at just one bubble and we try to see what's going on, you can realize that what matters the most in bubble growth or collapse, what is usually done, is actually not the fact that there is phase change happening, but what is mainly controlling the behavior is actually this aspect that they don't act as they don't act the same way. The compressibility is not the same. So, but still, we want to add phase change. What is done today is only infinite phase change, so we know it won't work because you just add even more matter to expand. So we want to have a finite phase change and to have viscoelasticity in the model, so we can then have the gel and see if this has some influence on the shock-induced cavitation. All right. Sorry if it was a little long. Thank you. And yeah, there's a lot of collaboration on all the work that I introduced. So it's not only my work. I can you can trust me. There's a lot of work being done here. So I thank everyone. Yes.
Okay, so it's a very interesting talk. Thank you very much. And an interesting aspect you're certainly aware of is that my neighbor here, Stéphane Populaire and Daniel Fuster, have also a model of cavitation, and that involves not the 4, 5, 6, 7 equation model, but involves just a sharp interface simulated by volume of fluid with a sharp transition from for the densities and everything else. And so these are very different models, and the majority of the cavitation studies are made with the I don't know how to call them. I think Sorel, Abgral were among the first to develop these models, but they were other people before, Baron and Seattle, and maybe others. So really, I don't know how to call these models. These models were a huge improvement because 30 years ago, if you try to do that, the code would explode at the second time step.
Yeah.
But then Sorel solved that problem. I think he says he solved it. I mean, sorry. Just
I will say with Rémi Abgral, I would say.
And anyway, so some people solved that problem, and so here you are. But they still these models are hugely different from the model that from Daniel and Stéphane, which also works. So, what's your opinion? How do these models compare? I mean,
yeah, well, I'm trying to respond to this question every day, but what is sure is that I don't exactly know why they are both working in a context of when we track the interface, right? Because what I presented here is mainly mixture appearing, so it's like cavitation appearing within a mixture. So I think sharp interface, you could do that, but you will need to model all the nuclei, and that's, I mean, it's basically impossible, right? but theoretically you could. So that, for sure, that's one of the difference. And that's discussion we had for years with Daniel, actually, because I know more or less why mine is working so well. I don't super perfectly understand why yours is working so well, and inversely. And so we are trying to figure out, okay, why things are working this way, and why are just like, it's kind of like a beautiful thing that they both work, although they are different, really different approach in terms of like way of thinking about the problem. It's very different. So I guess the main reason for those specific aspects, for like just a bubble that you track the interface, is that it's mainly governed by the fact that the phase on the pure sides, it's a difference of compressibility between the phases, and not really what happened at the interface, but more like, okay, on the big picture, energy-wise, I mean.
What I see as a possible explanation that both model works is that both models share one common point. They have a relaxation equation for the pressure. You agree, Stefan?
Yes. Well, I agree. Yeah, I mean, it's important, as you showed, it's important to have this relaxation time. One difficulty maybe is what you showed also, is that this relaxation time includes a lot of physics, which is at the moment modeled in a very crude way. I think you would agree with that.
Yeah.
For example, you explained how you introduce the product of the volume fractions, but you could say, okay, why is it the product, right?
Exactly.
Why not some pair of the volume fraction, whatever. And the point is that the fact that you have this thick interface, you want to model dispersed phase, but you also want to model interfaces. So you could say, well, is the relaxation time the same in both cases? Probably not, most probably not. So what you use for an interface should not be the same as what you use for a bubble cloud and so on and so forth. So I think there are, a lot of questions which are, as you showed, are linked to how you describe or try to understand this relaxation time. Yep. So maybe a question related to that. Do you think that looking into, you could do that either doing experiments as you showed, but of course it's hard to control the detail of these transitions, right? And so do you think there would be other ways, maybe also based from first principles, to better understand this particular relaxation time and how it should relate to, for example, the volume fractions or other parameters?
Yeah, that's a good question. It's so yeah, so your first point is like, okay, so yes, they are not behaving the same, the interface, and that's why we came up with this new formulation, and it worked pretty well. Although we want to continue like to study this aspect, right? So the based on what we want to do with experiments. So basically, we're going to do like a tower that drops like some a tube, like conic tube, so you have tension, and based on this, we can vary the velocity of the tube, and we can vary the mixture within the tube, so we can observe like maybe better understand what happens in terms of mixture behavior, right? Even if we don't relate this to the modeling, just okay, what is happening in terms of experiments, right? Because actually we don't know. I mean, there's nothing on this on the literature basically. So we want to do this, and the point of like, okay, is there like an analytical way, some kind of analytical way to find this? I mean, it's been several years that I'm thinking about this actually, and I guess there must be, but we didn't find it yet. I just don't know how to tackle the problem actually in terms of analytical solution.
Any other questions or comments? Okay, I have just one for you. It's naive perspective. Well, you presented some experiments with cylindrical droplets.
Yes.
How do you do the cylindrical droplets?
It's
in true experiments?
Yeah, sorry. So you take, usually it's better to use glass. Sometimes they use plexiglass, but it's not really great because of the well, it does respond too much of like the waves you send through. But you take two glasses basically, and then you put a small droplet in there. So obviously the droplet is not perfectly drop because it stays here because of surface tension, right?
Okay.
But then you have like a small curve,
okay,
right?
Okay.
But if you
Meniscus,
find a good
okay.
distance, you have the curve that
I
is
see.
almost straight, and
Okay.
it's okay.
And it's in another point is when you look at your pictures, the interfaces it doesn't seem to change.
Which one you mean?
Well, here, well, yes, this one.
This
yes.
one? Yes.
If you look at the, you would
So this I didn't mention, but so this side is the experiment. So same here. It's between two glasses, and you see what I just talked about, the fact that there is some curve, right, of the interface because of surface tension. So it's not a pure cylinder, right? It's a little curved. So this is why you see this thickness here.
Oh, so it's moving there inside.
So it's not because it's moving. It's just because if
Yeah,
you
okay.
here it's view from the top. If you add from the side, you will see something like this, let's say, and the two glasses here. So that's why you see some thick interface here. But if you we don't see it really well here, but here, I mean, it's somehow enhanced, but it's kind of sharp interface.
Okay.
In the simulation, it's not the case in experiment, unfortunately. So that's also why when you look, we don't see it much here, but when we look at those experiments here, you see other waves, right? It's kind of a mess. We see the important waves, but there is also other things, and those other things are just coming because the interface is curved. There's also the glass, so it's not perfect.
Yeah, well, that's life. Okay, any more comments or questions? If not, let's thank you once more.
Thank you.